that the chi or the launch angle, the line of sight angle is a state, and the control will be to control the change in the line of sight. So the change in distance between the threat and weapon can be expressed in a mathematical relationship, which is a function of the horizontal and vertical displacement changes, the velocity, and also the line of sight angle. The change in line of sight also can be represented by a particular mathematical relationship, and I chose the control variable to be the missed distance between the interceptor and the threat. And I have defined it as y, and y is a function of the the line of sight angle, and also u, which is the control command input. This is the system block diagram, where you can see the dynamic inversion is applied to the closed loop system, and information of the trajectory is sensed by some remote sensors and fed into the system. So in the end, what it is doing is it is getting some measured values, it has a command input, and it is generating the error signal, and with time we are trying to drive this error signal to 0 to get the desired output. I will now go through the results. So this is a simulation snapshot which was implemented in MATLAB, and as you can see, this is just gives a scenario where the ballistic missile was intercepted. The red color line shows the ballistic missile flight path, and the green shows the interceptor flight path. The diagrams below show the sensitivity of the constraints, and it is shown that a feasible interception has occurred. So I have done several simulations, I have run several simulations and obtained numerical results. This is my system design in MATLAB, which was implemented in Simulink. So again, I'm not going to dwell much on this particular path, but here I was able to get the system dynamics and the control command and design an integrated system and finally see how the system is behaving. These are the numerical results for the trajectory, where you can see the highlighted parts are the best results achieved at a launch angle of 45 degrees and a reasonably high velocity given in kilometers per second. And the red color ones, that is when the velocity was lower or the launch angle was around 90 degrees, the constraints were violated, so those are not the feasible results that we want. These are the simulation results of Simulink. This particular case was for a velocity of 4 kilometers per second and a launch angle of 45 degrees. You can see how the range is, that is the distance between the interceptor and the threat is reducing, and the missed distance also has reduced over time, and the control command is the most important thing. At first we have had to give some command, but as time went on, the amount of input or the magnitude of the command input has reduced, which means we are achieving the desired dynamics. This is how the line of sight angle is changing. So over a certain period of time, the change in the line of sight has gone to 0, which means once the target is locked, it will keep it in that particular angle until the interception is occurring. So it more or less resembles a proportional navigation controller. This is when the adaptive control part came into play, where I gave a disturbance. So this disturbance is just a random disturbance, can represent aerodynamic loads or gust wind forces or any other external disturbance that the interceptor may face during its flight. So depending on the disturbance, the command input will also change in order to get the system desired dynamics. And again, the line of sight angle and the change in the line of sight angle is also remaining more or less around 0. The change in the line of sight will remain more along 0 with slight disturbances due to the wind forces. So discussing about what we saw in the diagrams, the simulation more or less delivers intuitive results. That is, The time to intersect depends on launch angle and velocity. It is an obvious fact, and higher the velocity, the quicker the intersection will be. So that basically validates the simulation. This system can be modified to get desired dynamics or best results. According to your requirement, you can change the simulation. Once the target is locked, the line of sight will remain constant until intersection. So as I said, it is resembling a proportional navigation controller. The control variable was the miss distance, and the control law was KPN times the change in the line of sight angle. So this KPN value is, I have defined it as 4. Depending on the type of guidance, here I considered only a passive homing guidance. For an infrared seeker, this value will be around 4. So depending on what type of guidance you have, the value of KPN will differ. These are my assumptions and limitations. I looked only at a two-dimensional case, and the threat, being a ballistic missile, had very limited amount of maneuverability. I neglected the effects of Earth's rotation, and all results are based on computer simulations, since no hardware experiment was possible at present. The outcome of this research is that I demonstrated a practical optimization algorithm for the assessment of an integrated missile interceptor control system. This design was able to adapt to different perturbations that may occur in the trajectory, delivering a quicker interception. This will definitely prove valuable in designing hardware for interceptor control systems in the future. To conclude my presentation, in this research, what I did was I optimized a basic trajectory in a two-dimensional setting, and the control law was designed using dynamic inversion and adaptive control. This simulation showed good tracking and delivered optimum results. And as I said, it will render improved performance of integrated interceptor control systems, where hardware design will be backed by this particular computer simulation. So I have come to the end of my presentation, and I would like to acknowledge people who have helped me to do this research: my mentor, Lieutenant Colonel Paul Blue of the United States Air Force, Mr. W.S.P. Fernando of the Department of Mechanical Engineering, who was kind enough to review my paper, my HOD, who was very supportive to me towards the end, and also the authors of all the referred work, which in my literature review. So, that is the end of my presentation. I thank you all for your attention.